Welcome everyone! NVIDIA has announced a major leap forward in AI hardware with its new Rubin platform expected to arrive in 2026. Designed to follow the Blackwell generation, Rubin introduces substantial improvements in processing, memory bandwidth, and overall system integration. These upgrades are tailored to meet the growing demands of artificial intelligence, which now requires unprecedented levels of computing power to support next-generation models. From massive language models to real-time multimodal AI assistants, Rubin is engineered to handle them all with speed and efficiency. At the heart of this new platform is the Rubin GPU, which builds directly on the success of the Blackwell architecture. The Rubin GPU features an improved layout with more densely packed processing cores, especially NVIDIA's specialized tensor cores. These cores handle matrix multiplications, which are fundamental to deep learning tasks. The more efficiently these calculations can be done, the faster models can be trained or deployed. Rubin increases the core count and optimizes the core scheduling for greater throughput per watt of power consumed. This means not only better performance, but also lower operating costs for companies running large-scale AI systems. A standout upgrade in Rubin is its adoption of HBM4 memory. HBM stands for High Bandwidth Memory, and the fourth generation of this technology delivers major increases in both speed and capacity. The memory modules are vertically stacked and located extremely close to the GPU itself. This setup allows for much wider and faster data transfer compared to traditional memory like GDDR or DDR. In AI workloads where large models constantly stream enormous amounts of data, memory bandwidth becomes critical. HBM4 feeds the GPU at a faster rate, keeping processing cores busy and reducing idle time. The result is faster training times and the ability to handle models with trillions of parameters more efficiently than ever before. In addition to the GPU improvements, Rubin also includes the Vera CPU, NVIDIA's next-generation general-purpose processor. The Vera CPU builds on the Grace architecture and is optimized to work closely with the Rubin GPU. While the GPU handles parallel computation, the CPU takes care of system-level tasks, such as managing memory access, orchestrating compute resources, and running background operations. In high-performance AI servers, this coordination between CPU and GPU is vital to prevent bottlenecks. Vera's improvements focus on minimizing data transfer delays and ensuring the GPU always has the data it needs when it needs it. Connecting the GPU and CPU together is NVLink 6, NVIDIA's newest high-speed interconnect. NVLink 6 allows Rubin systems to achieve very high data throughput with extremely low latency. When multiple GPUs are working together, as they often are during model training, NVLink 6 ensures that these processors can share information quickly and remain in sync. Older connection standards like PCIe simply can't move data fast enough to keep up with Rubin's compute capabilities. NVLink 6 is essential for scaling up AI systems that require dozens or hundreds of GPUs working in parallel. Beyond the core processors and interconnects, Rubin introduces new networking hardware that enhances its data center performance. This includes the latest versions of InfiniBand and Spectrum-X Ethernet, along with the CX8 SuperNICs. These technologies manage data traffic between servers, ensuring that large AI clusters operate smoothly. As AI systems grow more autonomous, the Rubin platform is likely to play a pivotal role in supporting decision-making at the edge, in places far from traditional data centers. Rubin's modular hardware could be embedded in systems like remote drones, offshore oil rigs, or autonomous research vessels where intermittent connectivity demands local computation. By equipping these platforms with high-speed memory and optimized compute capacity, Rubin allows AI models to function independently, making complex judgments without constant cloud access. This shift toward localized intelligence marks a fundamental change in AI deployment, where decisions once reserved for centralized servers can now be made instantly on-site. Rubin also integrates well with NVIDIA's software ecosystem. Tools like CUDA, TensorRT, and NVIDIA AI Enterprise are compatible with Rubin, so developers don't need to rewrite code when upgrading. This backwards compatibility is a key reason many organizations continue to invest in NVIDIA hardware. With Rubin, NVIDIA is also supporting new applications in multimodal AI. These are systems that combine voice, text, images, and video all in one model. For instance, Rubin can power a digital assistant that listens to spoken input, reads text on a screen, identifies objects through a camera, and responds with synthesized speech. Another underappreciated strength of the Rubin architecture is its potential to power real-time, closed-loop AI feedback systems. In areas like robotics, surgery, or precision manufacturing, AI must not only make predictions, but also act on them immediately and adjust based on the results. Looking ahead, Rubin sets the stage for even faster progress. NVIDIA has already announced Rubin Ultra, expected in 2027. It will include more HBM4 stacks, improved interconnects, and further enhancements to core architecture. This rapid release schedule, a new platform every year, reflects the explosive growth of AI development. For cloud service providers, Rubin offers new ways to scale infrastructure. Data centers running AI as a service will benefit from the increased density and efficiency of Rubin-based systems. These servers will use less power, occupy less physical space, and deliver more computing output per dollar spent. Rubin will also help accelerate AI in fields like healthcare, where real-time image analysis, protein folding simulations, and patient record processing require huge computational power. One forward-looking application for Rubin could be in AI-generated simulation environments, entire digital worlds created and managed in real time for purposes like autonomous vehicle training, synthetic biology modeling, or defense scenario planning. These simulations require fast rendering, dynamic input-response handling, and continual recalculation of complex physics or behaviors. The Rubin platform is named after Vera Rubin, the astronomer who confirmed the existence of dark matter. It's a fitting tribute. Just as her work revealed hidden structure in the universe, NVIDIA's Rubin may help uncover patterns in massive data sets that were previously too complex or too large to explore. Rubin represents more than just a performance upgrade. It symbolizes the next stage of AI computing, one that reaches deeper, moves faster, and supports a broader spectrum of real-world applications. Thank you very much for watching. Please like and subscribe.